Hello everybody, this video is going to be about polarity. In this lesson we're going to learn that not all molecules are perfectly symmetrical, and when they're not symmetrical you can end up with a situation where the electrons are not uniformly spread out over the entire molecule. That can really change how things behave, it can change their properties, and then we'll learn a little bit more about the implications of those changes to properties in another video. So during this lesson, we're going to use polar bears and penguins for a little analogy, okay? So we're going to look at molecules like oxygen gas and hydrogen gas first. In these molecules, the electrons are being shared equally. When you have oxygen gas, you have two of the exact same atom bonded together. And so neither of those atoms is more or less electronegative than the other. One oxygen is not stronger than another oxygen. So when they're sharing those electrons, the electrons will be distributed equally between those two atoms. Neither atom is hogging the electrons more often than the other. So you can see in the picture, the polar bears are sharing that ice cream cone nice and evenly. Same with the penguins. Hydrogen is not as electronegative, so the penguin is smaller and not as strong, right? So hydrogen, not as electronegative. But you can see because it's two hydrogens, they're still sharing that ice cream cone equally. The electrons would be nice and uniformly distributed. However, if you look at something like HF, that's when we're going to start seeing something called a polar molecule, where things are not being shared equally. Here, it would be the equivalent of a penguin trying to share the ice cream cone with the polar bear. They're sharing, technically, that penguin still has his hand on the ice cream cone, but you can see that the ice cream cone is going to be closer to the polar bear more often. Right, the fluorine is more electronegative, so the electrons are going to end up pulled in that direction more often. So we say that there's more electron density around the more electronegative element. So fluorine will basically be hogging the electrons. So you can see in this little picture, we represent that sometimes with an arrow like this. We end up with a little bit more positive characteristic on the hydrogen side and a little bit more negative over here on the fluorine. It's not a full positive, it's not an ion, right? But it's just not quite as equal. This side is a little more negative. So we point the arrow in that direction. When you have molecules with more than two atoms, you have to start looking at their three-dimensional shape, right? That's why we learn Vesper, is because it's going to change where the electrons are. So water, for example, we have to remember that water is bent, okay? We have an oxygen, and then the hydrogens are bent down below. So if we were to look at our polar bear and penguin analogy, we have an oxygen polar bear, and we have two poor little penguins down here, two hydrogens down here. You can see that the oxygen is pulling harder on the electrons because it's more electronegative for each of these bonds. This bond is polar, right, because it's not being shared equally, and the molecule altogether ends up polar because we end up with one end of the molecule very different than the other end of the molecule. So we have our polar bear tugging on these poor two little penguins. You can sometimes also see this represented in kind of like a bubble notation, where they try to draw like a bubble around the molecule in 3D kind of shape, and then they color code it with a little key down below telling you which color is more negative than the other. That style of representing the polarity is a little bit hard to do on your paper trying to accurately shade that and trying to draw it 3D like that's a little bit tough. So we almost never do that. We typically will use like the arrows to represent it. Much easier. All right, now let's look at something like carbon dioxide, because carbon dioxide is going to show us that there is a difference between a polar bond and a polar molecule. Okay, so carbon dioxide, we have poor little carbon is the penguin, and we have two strong polar bear oxygens, one on each side. Remember that carbon dioxide is a linear molecule, right? It's straight. So that carbon, that poor little penguin, is being pulled in equal and opposite directions, isn't it? So we end up with this poor little bond over here being polar and this bond over here being polar. But the molecule overall ends up looking symmetrical because the left is the same as the right and the top is the same as the bottom. If I were to look at this molecule, the left side over here would have equal electron density compared to this side. If I were to flip this molecule over, it would look identical, right? The top looks the same as the bottom. If I were to flip it, it would look identical. So we say that symmetry can destroy the pole. It can cancel out that polarity that you might think exists by looking at the bond only. So you got to be really careful when we ask you questions, because sometimes we may ask you about whether a bond is polar or not, and sometimes we may be asking you if the molecule is polar or not. So be a little bit careful about that. So here's some examples. The top ones have polar bonds, and the molecule itself ends up being polar. So over here, HCl, right, the chlorine is more electronegative, so this right-hand side is going to have more electron density. It's not the same on each side. Over here, the nitrogen also has a lone pair up here, right? So it's really electron dense. The top looks very different than the bottom. CH3Cl, right? The bottom and the top are very different. The electrons are going to be drawn up towards the chlorine because it's more electronegative. So these all end up being polar. The electrons are not distributed evenly. Down here, BF3, well, fluorine's very electronegative, so it's going to pull the electron density towards the outside. This bond is polar, but because the top and the sides and the bottom, this all ends up very symmetrically distributed. Even though it's heavier on the outside, it's uniform, right? If I were to flip this molecule over, it would look the same. So the molecule is nonpolar. Same over here with CCl4. Yes, this bond is polar. Yes, the chlorine is pulling the electrons out towards this way. But if I were to flip this over, it's the same everywhere. So the molecule ends up being nonpolar. So in order to look at the polarity of the molecule as a whole, you first have to check to see if it has polar bonds, right? Then you have to look at the three-dimensional Vesper shape, and you have to see whether or not it's symmetrical. If you're good at visualizing things in your head, 3D, that might be really easy for you. Some people have a really hard time with that. So sketching the shapes out and drawing your arrows can really help if you have a hard time visualizing it in your head. I'm just going to show you kind of a couple of ways that you can diagram this polarity, what we call the dipoles. You've seen the arrow method. You could draw it for each bond, Or you can just draw one big arrow for the whole molecule. I like doing that because it's not as messy, right? It's a lot faster. Down here, you see the bubble method again. And then this is the way I really like. I like drawing what we call partial positive and partial negative. That's another way you can diagram it. Okay, make sure that when you're doing your diagramming of these dipoles, that whichever way you're doing is very, very clear. I can only give you points if I can understand what you're trying to convey, right? If it's messy or squished or, not obvious, then I can't give you credit for that. All right, sometimes people like seeing this idea in like a flowchart format. So if this helps you, great. If not, oh well, okay. You don't have to use the flowchart. It's just another way of thinking about it. So first question is, are there ions? Well, if there's ions, it's ionic and we're all done. There's no polarity. It's ionic. It's its own thing. Okay, polarity is really only for the covalent molecules. So if there's no ions, then it's covalent. Next question, are there more than 2 atoms? If there's only 2 atoms, then you ask yourself, are they the same element? Like O2, or H2, or Cl2, or F2. If they're the same element, it has to be nonpolar, right? It's like the 2 polar bears bonded or the 2 penguins. Neither is stronger than the other, right? So it would be nonpolar. If you have any difference in the atoms, like you have HF, right, or you have HCl, right, anytime you have 2 atoms that are different, then it's going to be polar. The penguin and the polar bear combination. If you did have more than 2 atoms, then you got to start looking at the Lewis structure, right? You got to start thinking about the Vesper, the 3D shape, okay? If it's symmetrical, it's nonpolar. Remember, the symmetry destroys and cancels out any polarity you might have. You may have polar bonds, but your molecule will be nonpolar. If it's not symmetrical, then by definition it's polar, right? If it's not symmetrical, you can't have an equal distribution of electrons. So in that case, it would be polar. Okay? All right, everybody, I hope that was helpful. Bye.